Math 2414, other convergence test, video 6, the limit comparison test. At the conclusion of the previous video, we had a series, this one, that we tried the comparison test on and we failed to draw a conclusion because the way we had set up our comparison, we had the series that we were looking at, that guy over there, as the ceiling, and we had a floor below it, but the floor converged. And it means nothing about the ceiling. The ceiling may converge, it may go up to infinity. So the comparison test was inconclusive. But we're going to use a new test called the limit comparison test. And it goes something like this. Suppose you have two series, so some of some A's, some of some B's, whose terms are eventually positive. Now notice that the hypothesis for this does not require some sort of dominant relationship where one of them is always greater than or equal to another. That goes out the door. All that's required is that at some point all the terms are positive. So we define a limit, which we call capital L, to be the limit as the n approaches infinity of the ratio of their individual terms. Now, one thing worth pointing out is it really doesn't matter which one goes on top and which one goes on the bottom. So it could say the nth term of the B series over the nth term of the A series. It really doesn't matter. It's arbitrary which one you call A and which one you call B. But let's say that we find the limit of that ratio. We're comparing the individual terms and taking their limit. Then we can draw a conclusion based on that limit. If the limit L is positive and finite, let that sink in, positive, but it doesn't go to infinity, then either both series converge or both series diverge. In other words, the two series do the same things. It is worth pointing out that if that limit is 0 or that limit is infinite, then this test is inconclusive. All right, so we're going to attempt that. We're going to attempt the limit comparison test on the problem that we left off with last time. So when we compare this to something, we don't have to worry about who's larger or who's smaller. We simply have to compare it to something that we know about. So we're still going to compare this to 1 over 2 to the n, the sum of 1 over 2 to the n. And I want to remind you that this is the same as the sum n equals 1 to infinity of 1/2 to the nth power, which is still a convergent geometric series because the ratio is equal to 1/2, and more importantly, the absolute value of the ratio is less than 1. So we already know what this series does. If we can set up the ratio, take the limit, and that limit is positive and finite, then we'll instantly know that the first series converges as well. Let's clarify what some things are here. We'll call this first one AN. So AN is 1 over 2 to the n minus 1, and we'll call the second one BN. You don't have to pause and say, you're A and you're B. I'm just saying, here's the pieces. We're going to set up the ratio whose limit we will take. Our limit, our L, is going to be the limit as n goes to infinity of one of these on top of the other, and it really doesn't matter which one you put where. But we'll put the first one on top and the second one on the bottom. Now, being fractions and on top of each other, we can just multiply the top times the reciprocal of the bottom. So I'll just describe it without writing it all. We're going to multiply the top fraction by this fraction upside down. Then we'll put the 2 to the nth power on the top, and we'll get something like this. 2 to the nth power over 2 to the nth power minus 1. If we did direct quote-unquote substitution with infinity, we would get infinity over infinity, and we could use L'Hopital's rule if you remember how to take the derivative of 2 to the nth power. But I want to show you another trick. Anytime your variable's in the exponent and you have a ratio like this, the trick is to multiply both sides by the ratio of by the reciprocal of the highest power, which in this case is the only power. But what you're accomplishing by multiplying both sides of the fraction by the reciprocal of the highest power is you're moving every single exponent into a denominator. Well, the numerator just becomes 1, and in the denominator, we distribute, and that will give us 1 minus 1 over 2 to the nth power. But what I meant was when you multiply both sides of that fraction by the reciprocal of the highest power, the end result is all of your powers will wind up at the bottom of little fractions. In this case, it winds up here. Now, why is that good? Because anytime you have a fraction whose numerator is constant and whose denominator is going to infinity, that fraction collapses to 0. And so our limit is 1 over 1 minus 0, which is a fancy way of saying 1. And notice that this limit is finite, symbol up, and positive. So according to the limit comparison test, since L is finite and positive, that means our two series do the same thing. And since we already know that the one we're comparing it to converges, then the conclusion that we draw is that the original series converges as well. Therefore, the sum 1 over 2n minus 1 converges by, and to abbreviate it, LCT, limit comparison test. Didn't have to worry about which one was greater or smaller. We just had to form the ratio, take the limit, get a finite positive limit, and then conclude that the two series do the same thing. All right, let's take a look at one more. This one's a little junkier, and I actually made this one up, but don't worry, I've given it a trial run, so I know it's going to behave. But the reason I wanted to do this one is that to show you that comparison, the straight up comparison, not limit comparison, is not always the most obvious thing. I got a toolbar I'm moving to. Because the recommendation on forming a comparison when you have a ratio of polynomials, and technically this isn't a polynomial, because your variable's in the exponent. But whenever you have multiple terms, a good series to compare it to is the series you get by removing all but the biggest powers. So removing everything except that. And if we kept those, we would get e to the n for e to the 2n. And we have an exponent rule that says we can subtract powers. N minus 2n is negative n. But this is the same as the sum n equals 1 to infinity of 1 over e to the n. And so again, this is a convergent geometric series. Convergent, we'll put GS for geometric series because our ratio is 1 over e. E is about 2.7. And so the absolute value of the ratio is less than 1. So we already know that the series we're comparing it to is convergent. So if our limit comes out to be positive but finite, then we instantly conclude that the original series is also convergent. It's kind of in the way no matter where I put it, so we'll just put me down in the corner. Okay, so let's form our limit. Limit as n approaches infinity. And let's be a little bit efficient with this. We are about to put this on top of that, or vice versa. Which means that one is going to get multiplied by the reciprocal of the other. By the way, when we get to this video about the ratio test, we'll be putting fractions on top of each other so often, you're going to instantly just multiply one by the reciprocal of the other. So instead of putting one fraction on top of the other, let's go ahead and just write it as 1 times the reciprocal of the other. And it doesn't matter which one you reciprocate and which one you don't. So let's leave the original series argument the same. And if we put that on top of the new series argument, then that would get reciprocated. So we're turning the one in the green box inside. E to the 2n over e to the n. Let's distribute across the top and across the bottom, just to turn it into a single fraction instead of a product of fractions. Now keep in mind, when we distribute, we can add the exponents. So on the top, e to the n times e to the 2n is e to the 3n, plus 1 times e to the 2n is e to the 2n. And on the bottom, e to the 2n times e to the n is e to the 3n. Remember, we're adding exponents. Plus 1 times e to the n is e to the n. Keep getting in the way no matter where I go. All right, so now we have this, and how on earth do we take this limit? Well, it's infinity over infinity, and you can try L'Hopital's rule, but the e's aren't going anywhere. When you take the derivatives, they're going to sit there and just pick up more numbers in front when the chain rule gets executed. So we'll still have infinity over infinity. But remember the trick I mentioned back here? Right, let's highlight real quick. The trick that redo please. 1 second, folks. All over the place here. The trick that I mentioned here, that when you have a ratio of things with exponents, and you're taking a limit as the exponent goes to infinity, try multiplying both sides of the fraction by the reciprocal of the largest power. Because if we do that, largest power is e to the 3n. So if we multiply both sides of this ratio by 1 over 3 e to the 3n, e to the 3n, and distribute, what do we get? Well, on the top, when we distribute the fraction of the first term, everything cancels and it leaves a 1. And when we distribute to the second one, we get e to the 2n over e to the 3n. But if we subtract those, we get e to the negative n, which is the same as 1 over e to the n. On the bottom, when we distribute, right here, when we distribute, on the first term, e to the 3n times 1 over 3 to e to the 3n is still 1. And on the second term, we get e to the n over e to the 3n. But again, we can subtract the exponents, get e to the negative 2n, which is the same as 1 over e to the 2n. All right, so let's clean this up just a little bit. Let's get rid of these parts here. And again, the advantage to multiplying both sides of the fraction by the reciprocal of the highest power is that all the remaining powers will be in denominators of fractions with constants. Draw, please. All the remaining powers will be in fractions whose numerators are constants. And so as n goes to infinity, both of those fractions collapse to 0, which means this limit equals 1 plus 0 over 1 plus 0, which is 1. That limit is finite. I gotta look at the camera when I'm looking here. That limit is finite. That limit is positive. And so by the limit comparison test, both series do the same thing. So the conclusion that we can draw is the original series, the sum e to the n plus 1 for e to the 2n plus 1 converges by the limit comparison test. I thought about doing a third example where we conclude diverges, but it's the same thing. We would just set up the ratio of the terms, take the limit. If the limit is finite and positive, then both series do the same thing. We would just need a series up front that diverges instead of converges. Then we conclude that the original series did the same thing. All right. And this actually concludes what in our textbook is section 8.3. So if you're working at that homework, everything that you need from 8.3 is contained up to these videos. The next video begins the material from 8.4, but I'll still continue by calling it video number 7, other convergence tests, because 8.3 and 8.4 are both just about other convergence tests.